All right, we're going to continue on to 5.4, dealing with derivatives and integrals of exponentials with base e. And what you have learned today is this is hopefully the easiest section of chapter 5, because when we're dealing with the derivative of e to the x or the integral of e to the x, it's actually itself. It's e to the x. The only difference is when we have e to the u here. So when we have e to the u, and we want to differentiate with respect to x, this is going to end up being e to the u times u prime. Okay, so in these scenarios, you just got to, when you're writing the derivative, you literally will write what you see and then multiply by the derivative of the exponent. Okay, and however you want to rearrange that, if you want to write that as 2e to the 2x, by all means, you do you. Okay, so this is rewritten as e to the x to the 1/2. So if we're looking at the derivative here, this is just going to be y prime equals e to the square root of x times 1 over 2 square root of x. So however you want to rewrite it, feel free. I'm not really worried about negative exponents in this section, to be honest with you. The derivative for this one is kind of nice. It's just itself, e to the x minus 4, because the derivative of x minus 4 is just 1. Okay. This right here, you're going to have to be able to see the product rule. Got to be able to see the product rule. We got first function is e to the x, second function is ln of x. So this is going to be y prime equals first times the derivative of the second plus second times the derivative of the first. Feel free to rearrange that, again, however you want. This is also a product. Okay, x cubed is my first function, e to the x is my second function. So y prime equals first times the derivative of the second plus the second times the derivative of the first. Okay. Here we got a chain rule. Okay. So this is going to be this function right here is kind of like a composite function. This is what was placed into a u cubed scenario. So this is going to be our chain rule here. So the derivative of the outside is 3 squared. Leave the inside alone. And then multiply by the derivative of the inside, which is negative e to the negative t plus e to the t. So really the only difference between the derivative or the original and the derivative is this negative sign. We need to multiply by the negative 1 there. Okay. This right here, there really isn't a whole lot that we can do with this to manipulate it, right? So this really is just going to be like, hey, let this be u. So the derivative of natural log of u is u prime over u. So this is going to be 2e to the 2x all over 1 plus e to the 2x. Okay. For this one, some of you might look at this and say, oh, yeah, that's a quotient rule. And I'm like, but do we really have to use a quotient rule? To me, it's going to be very similar to this problem up here. I'm going to take this and rewrite it and write it as e to the x plus e to the negative x all to the negative 1. Okay. So now we go ahead and say, all right, what's the derivative here? This is going to be a chain rule. So y prime equals negative 2 to the negative 2. Leave the inside alone. And then multiply by the derivative of the inside, which is e to the x minus e to the negative x. And if you want, you can pull that down. And I got no issues with that. But I'm not really worried about writing about it right now. Okay. Number 9 looks intimidating, but in reality, you're trying to find the derivative of an integral, antiderivative here. So this is really the second fundamental theorem of calculus. 2 steps forward, 2 steps back. Okay. So our derivative of this is going to be, this is pi, which is a constant, and this is natural log of x. So substitute this in, and then go ahead and multiply by the derivative of that. This is going to be cosine of e to the natural log of x times 1 over x. Well, e to the ln of x is actually just cosine of x all over x. That's what that simplifies to. When you have e to the ln, you can just write what it is right there, that x. Okay, you just can't have a blocker in front like a scalar here. You would have to take that to the exponent before you simplify that. Okay, number 10. Again, remember what we're doing with these new functions, these transcendental functions. We are utilizing the same material from chapter 2 and chapter 3, just with different functions. So we're going to take these exponential functions with base e, and we're going to talk about, second fundamental theorem of calculus, chain rule, product rule, potential quotient rule. In this case, finding information about a tangent line. So what do we need? We need a coordinate, which we have here, and we need a specific slope at this x value. So the first thing I'm going to do is find the derivative. So this ends up being e to the 1 minus x times negative 1. And now I'm going to do f prime of 1 equals e to the 0 power times negative 1. And before you just write it off and say, oh, yeah, that's 0. Remember, anything to the 0 power other than 0 is 1. So this is actually going to be negative 1. So my slope is negative 1, and I got the coordinate x1, y1. So this is just point slope form. So your tangent line is going to be y minus 1 equals negative 1 times x minus 1. Okay. Página 2. Use implicit differentiation to find dy dx. So we got some x's and y's mixed together. That's implicit. So I'm going to differentiate with respect to x. So right here is a product rule. This is straightforward. This is going to be 3 dy dx. So first times the derivative of the second. So this will be e to the y times the derivative of the exponent with respect to x. And that's just the dy dx. So first times the derivative of the second plus second times the derivative of the first, which is just 1. Then this is going to be minus 10 plus 3 dy dx equals 0. So in this scenario, we want to add the 10 over and factor out a dy dx. So that's what this looks like right here. It's going to be dy dx. Lights go out. Lights come back on. We get x to the ey plus 3, because that's me just factoring out a dy dx from both the x ey and the 3 here. And then I need to move these two pieces of information over to the other side. So this is going to be 10 minus e to the y. So when it's all said and done, dy dx equals 10 minus e to the y all over x e to the y plus 3. Okay. Our use substitution with integration, okay? Some of this stuff's going to be pretty straightforward, but again, the antiderivative of e to the x is going to be e to the x. But if we have something like this where the derivative is something other than 1, then we're going to have to use substitution. So in this case, we're going to let u equal 5x, which would make du equal to 5 dx. And that's what I want to replace there. So this is just really going to be the integral of e to the u du, which is just e to the u plus c. And remember, indefinite integrals, you got to go back to your x. So this is just going to be e to the 5x plus c. Some of you can just see that right away. This, if we let u equal to 2x minus 1, du is going to be 2 dx, but you got to multiply both sides by 1/2. So inevitably, this is going to be 1/2 e to the u, which was 2x minus 1 plus c. Okay, in this scenario, let u be the exponent, and another way to tell why that's the exponent is this is a degree 3, that's a degree 2. Your u is usually 1 degree higher. So if we let u equal the x cubed, du equals 3x squared dx. But I want to replace x squared dx, so that's why I'm going to multiply both sides by 1/3. So then this ends up becoming 1/3 integral of e to the u du, which equals 1/3 e to the u, which is e to the x to the third, plus c. For this example, I'm going to let u equal x to the 1/2. So then that would make du equal to 1/2 x to the negative 1/2, or dx over 2 squared of x. If but I just want to replace dx over square root of x, so I would multiply both sides by 2 here. So then this would become 2 integral of e to the u du, which is going to be 2 e to the u, which was square root of x, plus c. I'm going to let the entire denominator be u here. Very rarely do we let, except for trig inverses, but very rarely we're going to let part of the denominator be u. So if we let all of this be u, the 1 plus e to the negative x. Be careful of that negative x. They're hoping you're going to forget it. This is going to be, the derivative is going to be negative e to the negative x dx. And so I got to multiply both sides by negative 1. So then this becomes negative 1 integral of du over u. So then we get negative natural log of u, which was 1 plus e to the negative x plus c. Here I'm going to let everything inside the radical be u. So if I say u equals 1 minus e to the x, well then du is just going to be negative e to the x dx, because that negative still comes into play there. Okay? So then I'll multiply both sides by negative 1. So this ends up becoming the integral of negative 1 u to the 1/2 du, which ends up becoming add 1 divided by the new, so negative 2/3 u to the 3/2 plus c, or better yet, negative 2/3, and our u was 1 minus e to the x to the 3/2 plus c. Cool. Here, very rarely am I going to let the numerator in a scenario like this be u, so I'm going to try out and see if the denominator, if we let u equal e to the x minus e to the negative x, so then du is going to equal e to the x plus e to the negative x, which is actually what my numerator is, which is nice. So inevitably, this is going to be the integral of du over u, and we know that to be the natural log of u, and u in this case was e to the x minus e to the negative x. Okay. Number 19, might get confused. Hey, what do I let u equal? Remember, this is inside another function right here, so I'm going to let u equal e to the negative x. So then du equals negative e to the negative x dx. So I'll multiply both sides by negative 1. So this is actually going to become the negative 1 integral of tan u du. And if you remember what we talked about a couple days ago, yesterday, whatever it may be, the integral of tan is negative natural log of cosine u. So this will become a positive natural log of cosine of u, which was e to the negative x, and then plus c. Okay. Sweet, we're getting places. Okay, we've got definite integrals now, so the only difference between the ones up here and this one is there are no plus c's, and we got to redefine our boundaries. So if I let u equal negative x squared, du is going to be negative 2x dx, but I want to replace x dx. So I'm going to multiply by negative 1/2. So this ends up becoming negative 1/2 integral of e to the u du. But now I need to redefine my boundaries. So I'm going to plug 0 in, I get 0. I'm going to plug 1 in, and I get negative 1. Okay, I no longer need to look at above the line. This is my new problem. So this is going to be negative 1/2. And if you want to, you could put 0 up here and negative 1 down here and make this a positive 1/2. I got no issues with that. This is going to be e to the u and then negative 1 and 0. So if we do it, we're going to get negative 1/2 times e to the negative 1 minus e to the 0. And before you say, oh, that's just going to be, remember, this value is 1. So in reality, this is going to be negative 1 over 2e plus 1/2, or some version of that, because this value right here is actually 1. Okay. Number 21, I'm going to let u equal, if I let u equal to x squared, that means that somehow I'm going to have to try and let du be some form of an exponent, and we know that's not the case. So I'm going to let u equal to 3x to the negative 1 here, which would make du equal to negative 3 over x squared dx. But I don't want negative 3x squared, 3 over x squared dx. I just want dx over x squared. So I'm going to multiply both sides by negative 1/3. So this integral ends up becoming negative 1/3 integral of e to the u du. My new boundaries, if I plug in 1, are going to be 3 and 1. So this time, let's go ahead and flip the boundaries and make it a positive 1/3. So this will be 1/3 integral from 1 to 3. Just a little bit scenario so you know how to do both ways like this of e to the u du. So if you want to do that, this is going to be 1/3. And then the antiderivative is e to u from 1 to 3. So at the end of the day, you're looking at 1/3 e to the third minus e to the first. Okay. Cool. Last page. Here we go. Not even going to come close to that 30-minute mark, I don't think, unless I just ruined it. Okay. All right. Find the particular solution that satisfies the given condition. All right. Cool. So in this scenario, we want to go ahead and work backwards. Okay. And so in that case, it's going to take a little bit of notation. We'll have better work with this when we look at chapter 6. But let's go ahead and try and figure this out. Okay. So if I'm given second derivative info and I have a first derivative point and a original function point, I really just need to look at this first. The derivative is going to equal the integral of sine of x plus e to the 2x dx. So whatever that antiderivative is, that's going to end up becoming my derivative. So if I do that, the antiderivative of sine x is negative cosine x. If I let u equal 2x, then the derivative is going to be 1 or 2, but I have to compensate for it, so it'll be 1/2. So this is going to be plus 1/2 e to the 2x plus c. And if that's my derivative, and I'm given derivative info right here, then I need to plug that in. So this is going to be 1/2 equals negative cosine of 0. Well, cosine of 0 is 1. So this is going to be negative 1. This is going to be plus 1/2 e to the 0, which is actually just 1. So this is going to be 1/2 plus c. So at the end of the day, c is going to equal 1. Okay, you subtract the 1/2 over, add the 1 over, you get 1. So f prime of x equals negative cosine x plus 1/2, let's see here, 1/2 e to the 2x plus 1. And so now if we want to find the original function, we can go ahead and take the integral of this right side. Okay, and so that's going to end up becoming negative sine x. This is going to need another scalar of 1/2, so this is going to be plus 1/4 e to the 2x plus x plus c. And I have the info of 0 and 1/4 here that needs to be plugged in. So this is going to be 1/4 equals sine of 0 is 0. This is going to be e to the 0, which is 1. So this will be plus 1/4 plus 0 plus c. So in this case, c equals 0. So the final answer here is going to be f of x equals negative sine x plus 1/4 e to the 2x plus x. Let me double check and make sure that's what I got years ago. Looks like that's what I got. Sounds good. Let's finish this last one. Okay. So, we got our equation here. This is actually a differential equation. So this is where we're going to have to take dx to both sides. So in reality, this is going to be dy equals 2e to the negative 1/2 x dx. Just multiply both sides by dx if we can do that. And it's just a magic show. We can do that. So I'm going to integrate both sides. This ends up becoming y. Yeah, it's going to be plus c, but I'm going to take that plus c and subtract it over to the c that's going to be on this side. And so c minus c is going to be another c. And we haven't implemented any points yet, so it doesn't really, I don't have to be specific with my c values yet. So then this is going to be u. So then the derivative is going to be negative 1/2. But I don't want to replace negative 1/2 dx. Like if we say u equals negative 1/2 x. So then du equals negative 1/2 dx. But I want to replace 2 dx. So how do I get this to be 2? Well, I'd have to multiply by negative 4 to both sides. Right? So this is going to be negative 4 e to the u plus c, or e to the negative 1/2 x plus c. And then I plug in my values, where I get 1 equals negative 4 e to the 0 power plus c. So in this case, this is going to be negative 4. I'm going to add 4 over, and I get c equals 5. So our final particular solution is going to be y equals negative 4 e to the negative 1/2 x plus 5. Double check here. Ooh, I love it when it works out. All right. So that should take you through 5-4. If you have